Yeah, our project is about removing reverb from sound. I'm Jakob. This is Oskar. So what is reverb? Just imagine you have a room like that with one person standing on a stage talking to another person in the audience. And then there's one way the sound could take. It's just a direct path. It's called a dry sound. And that's the sound without reverb. It might sound something like this. There's no reverb at all, but sound is not like just not like this. Oh. Okay, now this is not the only sound which arrives at the person in the audience, but you also have the sound which is reflected from the walls, and the reverb is just the sum of all the echoes reflected from the walls, and then this might sound something like this. So it sounds very different. Our task is to remove sound, reverb from sound, which means we start with something from the last sound example where we have a lot of reverb, and we want to end up with something where we don't have any reverb. So what are possible applications for this? First is speech transfer. Everybody has experienced that in a Zoom call, Skype call, or phone call. We have some reverb. And another possible application is music production. Typically in professional music productions, you record the sound in the studio where you have as few reverb as possible, and then you add reverb artificially in post-processing. That's the standard procedure in music production. So the tasks are a little bit different. So for the first task for speech transfer, it requires real-time sound processing, while for the second task in music production, you do not really need real-time processing, but you can actually do it in post-processing. And generally for speech transfer, the sound quality doesn't need to be that good. But for professional music production, you of course need a very high sound quality. So our task is to remove reverb from sound, but it's very instructive to understand how you actually add reverb to sound. So this can be done mathematically by a convolution. The convolution is shown as this mathematical formula on the right. It's quite a simple thing to do. Actually, so what you start with is anechoic sound, which is sound recorded in a quiet chamber or anechoic chamber. You see a picture of that down here. It's a special chamber which absorbs all the sound from the walls, such as that you don't have any reflections. And that might sound something like this. List 1. And then you do convolution with a so-called impulse response function. How does that sound? The impulse response function. Let's play it again. It's just a very short sound. You can record that, for example, by clapping your hands inside the room, and then you record the response from that clap. And this completely characterizes your room acoustics. And that's called an impulse response function. And it's really synonymous with reverb. Different reverbs correspond to different impulse response functions. And that's actually what we want to remove from the sound. So the impulse response function depends on really many things. It depends on the room size and the room shape. It depends on the position of the source and the receiver. And it depends on shapes and sizes of objects in the room. Everybody has experienced that. If you go into an empty room, the reverb is very different, the sound is very different than in a room which is full of obstacles with furniture and so on. So what are the strategies for reverberation to remove reverb from sound? We can distinguish two different strategies here. In one case, this impulse response function is known, which basically means you know the reverb, you know where the sound is recorded, you know the room acoustics. And then you can deconvolve the signal with the impulse response function. That's just mathematically just the inverse operation of a convolution. And it's mathematically not very simple to do, but it's well known how to do that. And this task does not require any neural network. The really hard task then is if the impulse response is unknown. So just imagine if you do a Zoom call or a phone call, you do that in a place where you don't know beforehand in which room it takes place. You don't know the room acoustics, you don't know the reverb, so the impulse response is unknown, and still you want to remove that somehow from the sound. And this is a task which can be done or can be tackled by neural networks. So then we thought about two different strategies to do that task. The first is to classify the unknown impulse responses with a neural network and then deconvolve with a known impulse response. I will explain that a little bit more in detail on the next slide. And the other approach is to predict the dereverberated signal directly with an autoencoder. Oskar will tell you more about that. So the first strategy we tried is dereverberation by classification. It works as follows. You collect this set of known impulse responses. From that, you generate your sound with reverb. Then you train a neural network for this impulse response classification, which means now this network can really recognize the kind of reverb you have in your sound. And then you apply this neural network to sound with an unknown impulse response. And to classify that means something like you determine the known impulse response function, which is most similar to the unknown impulse response function. And then actually you do a deconvolution with a known response function, or you take a linear combination of known response functions and you deconvolve your sound with reverb. So we tried that approach. It works okay with a small sets of impulse responses, but it's not that well. You actually, to make it work really well with a good sound quality, you would require a huge set of impulse response functions, and we are not really able to do that because you need big resources for that. Yeah, and the next part is about different autoencoders we tried.
So yes, and one of the reasons we took this project with audio is because we are music and audio enthusiasts, and also because almost no one is doing it. And why no one is doing it is actually because it's really, really hard. So why is it hard? We have an audio signal, and the audio signal, the quality that we are used to, requires at least 41,000 samples per second. This is a lot, and we cannot input such long vectors to regular neural networks, so a dense layer wouldn't work on that. So to work with audio for ML projects or neural network projects, we would need to compress the information to reduce the dimensions somehow. One way of doing it is to use short-time Fourier transforms, which will give us some spectrograms, which consists of complex numbers. So we have a frequency distribution in time, but represented as imaginary and real part. So we can reduce it further, taking a magnitude and logarithm and scaling a little bit the spectrogram, which is called a ML spectrogram. Then we get rid of the imaginary part of complex numbers, and this is great. However, we cannot go back from the ML spectrogram to STFT and back to audio. And this is a huge problem. It can be solved by some algorithms which have bad quality, or we can use neural networks that were already developed and deployed. But on the other hand, those are very slow. So we have some possible strategies to work with our problem of removing reverb. We essentially need to use some kind of autoencoder or autoregressive method, and autoencoder is architecture here, where we take as an input some sequence. We try to reduce representation of the sequence while having as much of a valuable information as possible. So then this compressed information will be decoded by a decoder to something that should be essentially the same or very, very similar to what we inputted, but without noise, maybe, if we train the network to do it without noise. In our case, we would like to have the output signal without reverb. So there are a few ways to go here. The most common is to work with ML spectrograms. So we can use autoencoder and then use something that can decode the ML spectrogram back to the audio, like waveguide, but this is too slow for real-time execution on CPUs. We could use wavegun, but it is still slow. then we can work directly on audio signal, and we've tried that with autoregressive models. So for example, LSTM gave us a very bad quality. Then we tried WaveNet, which is essentially 1D convolutions with some dilations, the special one, causal. And those are very slow converging. And also they gave us no reasonable results, no convergence at all wherever we tried. Then we have our own idea to use a wavegun, pre-trained wavegun. However, we wanted to use transfer learning to teach it to omit the reverb in translation. So only translate speech back to the audio and leave the reverb out. The last way we tried is to use directly STFTs, and this is something that almost no one does because it is thought that neural networks cannot deal with complex numbers and they get lost there. But first we need a data set. So we used the anechoic data set, as Jakob told us. However, we cannot use the whole data set with our all reverbs because we have somewhere 40,000 samples. And if you want to add 2,000 reverbs to every sample, the data set would be way too large. So we used data augmentation on the fly. And we have some target audio. We add some reverb on the fly, and we want back the target audio. We also take different frames in time from our data set. So every time it's a little bit different signal, a little bit different sample. We take convolved signal, and we add them together back with different proportions. Which is supposed to simulate how close we are to the microphone. If we are close, then there is more of the original signal. If it's far, then it's a lot of reflection there. And that was the idea here. But this makes our training to be very, very slow. I mean, not very, very slow, just slower than normal. So first, we tried this Melgan architecture that is actually very good in translating the ML spectrograms into audio. Let's see some example of a trained Melgan. So this would be speaker that the network has never, ever seen.
Corporate banking would be based in Edinburgh.
And now the translation.
Corporate banking would be based in Edinburgh. So
I don't hear any difference, so I think it's very good. So now we try to train it by ourselves, and it sounds somehow like this. This is input audio.
Printing in the only set.
This is our output from the network now. Yes, so after 600 or even 700 epochs, we didn't train it. Later, I found that you need at least 1,000 more epochs, and it would take somewhere 14 days on one GPU. So, yeah, we didn't do it. Although still, I think it is the most promising architecture to actually remove reverb and have a good quality. Then we tried something that could work really fast in real time on a CPU. So we tried to the regular vision autoencoder, which has as an input ML spectrogram, and as an output we want STFT. So both real and imaginary numbers are to be predicted. Then we want to do inverse STFT and get back the audio. So this sounds like that. First, I will give you the input, then output, and then how it should sound. Now the output of the network. and it should be the last sound. So not very good, of course, but that was, we knew that it's gonna work like that, because not a lot of people would try this. So our last idea was to use only STFT spectrograms. So STFT spectrogram is going as an input and output from the network. However, this time we also take a residual connections. So the input STFT will be element-wise multiplied with the output of the network. And here we wanted network to learn some operation that when you multiply it with the input complex number representing audio, that this operation could maybe remove some of the reverb. Let's see how does this work. So first we have our input audio with reverb. It will be only very short reverb. Now the output of the network. And how it should sound. So we can see that it's not too bad. Let's see. Actually, I did it remove reverb because it was short. It wasn't really obvious whether it does that. So in the slide, in the image A, we have input audio with reverb as blue and prediction, so the output of our network as orange. And we can see that blue signal has some reverb in between the words, and that our prediction does not have this reverb. On the slide B, we have a target as blue and prediction as orange. So it's close to the target, but not exactly what we want. As you could hear, there is too much of the signal cut from the voice, so the output signal is not as good as we wanted it to be. So again, Melga did not converge. Mel2 STFT did not produce reverb, but also no reasonable sound. And STFT, it's a proof of concept for us that you can work with audio with STFTs, which is very important because I don't think much people thought about it. And we think that maybe not for reverb, but for some other applications, it could work. So our conclusions are, in general, that we didn't have enough of reverb. 2,500 examples of reverb is not enough to sample the space of reverbs well enough for any of our applications, actually, to predict a reverb or to deconvolve it. The reverberation often leads to some distortions of noise, and therefore we should probably use several architectures or maybe some kind of digital signal processing filters, because there's a lot of them. And our outlook expectations for this project was actually not to remove reverb because we knew it's very, very hard. The convolution operation is not easy to revert. However, if it would work, it would be super great because it's not only reverb that you want to deconvolve. This microphone and all the audio equipment has its own impulse response also. And in the audio applications, you would sometimes want to get rid of the distortion that your microphone does to your signal. So that didn't work, but I think that the STFT network, when we work with complex numbers, could be way better to removing unwanted sounds like harsh or resonating frequencies on recordings, or noise, tape, hiss, clicks, and pops. Or also when we have recording in church, for example, great concert, and then there is someone coughing or children crying, or you hear some urban sounds on the recording. I think that the STFT might be even good at this kind of applications. Thank you very much.